Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. From previous course in Math 1, you studied how to find the tangent line which touch a curve in a specific point P0. Now we are going to introduce the tangent plane and differentials. So a tangent plane touches a smooth curve at a specific point P0 in a space. As you see in this slide, if we have functions r of gt plus ht plus wt is a smooth curve on the level surface, and fx, y, z equal c of a differentiable function f, then f of gt, ht, and wt equals c. Differentiating both sides in this equation with respect to t leads to the following equations: d by dt of f equals 0. So we can expand that using partial derivative by applying that partial f partial x times dj dt plus partial f partial y dh dt plus partial f partial z dw dt equals 0. So if we take the partial derivative in a single bracket and the differentiable in the second bracket, so partial f partial x times I plus partial f partial y times j plus partial f partial z times k times second bracket g dt times I plus dh dt times j plus dw dt times k equals 0. The first part we call it gradient f, and the second part is the derivative of dr by dt. Definition: the tangent plane at a point P0 on the level surface of a function f of x, y, and z equals c of a differentiable function f is the plane through point P0 normal to the gradient f computed at P0. The normal line of the surface at P0 is the line through P0 parallel to gradient f computed with respect to P0. Tangent plane to the function fx, y, z equals c at P0 x0, y0, z0 equal the first derivative of f with respect to x at P0 time x minus x0 plus the derivative of f with respect to y time at P0 times y minus y0, and the derivative of f with respect to z at P0 times z minus z0 equal 0. And normal tile surface at P0 is the line defined by these three values: x equal x0 plus f but derivative of f with respect to x at P0 times t, and y equal y0 plus first derivative of f with respect to y at P0 times t, and z equals z0 plus the derivative of f with respect to z at P0 times t. Now let us consider the following example. Find the tangent plane and normal line of the surface for the function f of x, y, and z equal x squared plus y squared plus z minus 9 equal 0, which we call it circular paraboloid at the point P0, 1, 2, and 4. To solve this example, first we should compute the gradient of f and evaluate it at the point P naught. So the gradient of f given P naught equal 2xi plus 2yi plus k at the point 1, 2, and 4, which can be simplified to get the equation 2i plus 4j plus k. The tangent plane is therefore, by the definition, is 2 times x minus 1 plus 4 times y minus 2 plus z minus 4 equals 0. Simplifying that, we get 2x plus 4y plus z equals 14. Then the normal line to the surface at P naught is x equal 1 plus 2t and y equal 2 plus 4t and finally z equal 4 plus t. The plane tangent to a surface. To find an equation for the plane tangent to a smooth surface z equal function of x and y at a given point P naught, where z naught equal f computed at x naught and y naught. We first observe that the equation z is equivalent to f of x and y minus z equals 0. Then the surface z equal f of x and y is therefore the zero level surface of the function capital F of x, y, and z, which equal f of x and y minus z. So we can compute the partial derivative of capital F as follows. Partial cap f with respect to x equal partial x of the function f of xy minus z, which equal the first derivative of small f with respect to x minus 0 equal first derivative of f of small f with respect to x, and the same we can compute the partial capital F with respect to y to get it as a first partial derivative of f with respect to y, and the same for z. Now writing the plane tangent function as before, we get partial cap f with respect to x computed at P naught times x minus x naught plus partial cap f with respect to y computed at P naught times y minus y naught plus partial cap f with respect to z computed at P naught times z minus z naught equals 0. And therefore this can be reduced by replacing the partial derivative of cap f with respect of partial derivative of small f. We get a partial derivative of small x with respect to x computed at the point x naught y naught times x minus x naught plus the partial derivative of a small f with respect to y times y minus y naught minus between brackets z minus z naught equals 0. And therefore we can get at last the plane tangent equation as follows. The partial derivative of small f with respect to x computed at x naught y naught times x minus x naught plus the partial derivative of of a small f with respect to y computed at y naught, x naught, y naught times y minus y naught, all minus z naught equal 0. Consider the following example. Find the plane tangent to the surface z equal x times cosine y minus y times e to the power x at the point 0, 0, 0. To solve this example, first we should compute the first derivative of f with respect to x and the first derivative of f with respect to y, and compute these partial derivatives at the point 0, 0. So for x, we get a partial derivative of a small f with respect to x equal cosine y minus y to power y times e to power x, and substituting x and y by zeros, we get a partial derivative of small f with respect to x at the point 0, 0 equal 1. Similar, the partial derivative of a small f with respect to y equal negative x times sine y minus e to the power x, and substituting x and y by zeros, we get the partial derivative of a small f with respect to y at the point 0, 0 equal negative 1. Substituting the tangent plane function, we get the surface as follows: 1 times x minus 0 minus 1 times y minus 0 minus z minus 0 equals 0, or we get x minus y minus z equals 0. Another example. Consider the following surface: f of x, y, and z equal x squared plus y squared minus 2 equal 0. As you know, this is a function of order 2, which we call it a cylinder function. And we have the plane given by g of x and y and z equal x plus z minus 4 equal 0. You know, it is a linear function in two variables. Suppose these two functions met in the ellipse A. Find the parametric equation for the tangent to E at point P node 1, 1, and 3. Solution. The tangent line is orthogonal to both gradient f and the gradient g at P node, and therefore it's parallel to the vector phi, which is gradient f times gradient g, the component of the vector v, and the coordinate of P node give us the lines. So we start computing the partial derivative of the function f with respect to x, y, and z, and computed each of them at the point 1, 1, 3. So we get partial f partial x equal 2x, computed at the point 1, 1, 3, you get a 2. And partial f partial y equal 2y, and computed at point 1, 1, 3, you get 2. And partial derivative of f with respect to z equals 0. Then the gradient of f equal 2i plus 2j. There is no z here. Also, the gradient, we can get the same or do the same for the function g, finding the first derivative or partial derivative of g with respect to x and z. You get g, and the partial derivative of g with respect to x equal 1, and the partial derivative of g with respect to z equal 1, and then the gradient of g equal I plus k. So the vector v is the multiplication of gradient f times gradient g equal 2I plus 2j times I plus k, which can write it as determinant of nine elements, 3 columns, 3 rows. I, j, k, first row, second row 2, 2, 0, third row is 1, 0, 1. So you computed the value of that determinant, you get 2I minus 2j minus 2k. Therefore, the tangent line is x equal 1 plus 2t, y equal 1 minus 2t, and d equal 3 minus 2t.